draw in a nifty little horizontal sliver and talk about the pressure on the horizontal sliver at an arbitrary point. You guys, the reason why I'm choosing a horizontal sliver, not a vertical one, because I think the pressure is going to be constant along the horizontal sliver, assuming delta y is really, really close to 0. If I had a vertical sliver, I'm in a lot of trouble. The depth changes. It's not a constant pressure. That's why the sliver is horizontal. And if you guys don't mind, to keep myself straight, can I label this point x sub I comma y sub I? What I'm going to do first is compute the area of the sliver. What I'm going to do second is compute the pressure exerted on the sliver. What I'm going to do third is look at the corresponding force on an ice sliver. What I'm going to do next is look at the Riemann sum, convert it to a definite interval. Let's do it. Let's talk about the area of the sliver. I think the area of the ice sliver is going to be the area of a rectangle, length times width. But you guys, wouldn't that be this times this? Be honest. That was a heavy sigh. How about this? Watch my fingertips. This length is x of I. So that's 2x of I. And this length is delta y, because a small change in y direction. Next, I'm in trouble. That delta y, you know darn well, is eventually going to be converted to a dy, yet again when I take the limit of a Riemann sum, so let's just deal with it now. I think if this is the relationship between x and y on the border curve in black, then I can reinterpret x sub I as nothing more than the square root of y sub I. Let's do it. I got 2 root y sub I, delta y. Now to compute the pressure exerted on an ice sliver, all I'm going to do is look at the product of my rho with my g, with the distance for which an ice sliver is below the surface. But I think that's nothing more than 1,000 times 9.8 times d sub I. Well, you guys take a peek at the picture. Don't you guys agree that with my black pen, that's d sub I? But d sub I is going to be interpreted as nothing more than the high y value of 30 minus the low y value of y sub I. And so I think my d sub I could be interpreted as 30 minus my y sub I. Next, I think the force exerted on an ice sliver could be interpreted as nothing more than the pressure exerted on sliver times the area of that ice sliver, which I think in this particular example is a product of these two beasts. Would that give me a 2 times 9.8 times 1,000? Yes?
Shouldn't the height be like 32? If that's
Oh, should
10
it?
meters, it should be 5. That should still be 25. And we're adding 5. Oh, it's 30. Never mind.
Yeah, just double check my
I'm
rhythm.
sorry. No, you're right. No, I was thinking of the other problem of the
With the spout,
Yeah.
right. In this case, I don't have a spout. I'm not pumping. Oh, you guys, I just messed up. What did I just miss? I got my pressure times my area. I guess I'm missing my 30 root y sub I minus y sub I root y sub I times my delta y. Did I miss anything? So, that being the case, I think the total force, by taking the limit of the Riemann sums of these s sub i's, is going to be nothing more than a definite interval with a constant out front, or inside, doesn't matter, times the integral of my 30 root y minus y root y. I'm integrating with respect to the variable y. Oh, shoot, I messed up. I lost my bounds of integration. What are they?
0 to 10. No, 15.
Say it again. Say it one more time.
It's 20 minus 5.
I heard that. Everybody.
I don't get it. Because you said the distance from the water to the top of the dam is 5. The total
I know,
distance.
but I think that's completely irrelevant. I think what you need to look at is this.
Okay.
So let's talk about how these rectangles are being lined up when it comes to the pressure, or the force, due to hydrostatic pressure on the parabolic portion. I think these horizontal slivers stack from a low y value of 1 to a high y value of 25. Because this is 5. When I plug 5 in for x, the corresponding y value is 25.
Well, what's that 20 at the top?
That's the width, sorry.
Oh,
My apologies.
okay,
That's what
okay,
you're looking at.
okay,
That's
yeah.
the horizontal width.
Okay,
of the top.
okay.
Now you have it?
Yeah.
Oh, shoot, we're not done. Yes, sir. Is that a word? That's force. The total force due to hydrostatic pressure, sir, I've completely changed the application. I'm no longer looking at a work situation. And by the way, sir, notice this too. The way I phrase the problem is how much force is exerted on the front plate of the dam, not how much work is required to pump water out of some kind of cylindrical can or some kind of container. Whole different issue. Man, you guys, do you agree that we are just not done? I computed a total force exerted on the bottom portion of that facade for the dam, but not the top portion. So let's talk about the top portion. I will mimic the work I have. I think even with a sliver way up here on top, actually I'll draw one in. Where's my red pen? This horizontal sliver. Here too, using the same logic, I think the area of that ice sliver is going to be computed by looking at the length times the width, but the length is nothing more than 2 times x of y. It doesn't change. The width is still going to be delta y. It does not change. And my issue of converting everything to y still does not change as well. It's just that how I convert the x of I to y of I, oh shoot, they might change. Because I think the boundary curve is no longer my parabolic curve. So let's talk about the boundary curve. Actually, let's not. Let's be more lazy. Let's talk points. Help me. Oh, hold it. Can I change colors just so you can see I'm doing something new? Where's the blue pen? Okay, doing something new. Somebody give me this point. 5. No, not 25. Somebody give me this point.
What's the equation on that?
I don't have it yet. That's what I'm trying to get. Ten, 30. Are you there? Now to come up with an equation for this blue boundary linear expression. It's just a line. Got the equation line. Using my math skills, I will look at my y minus y sub 1 being equal to m times x minus x of 1, where in this particular case, m is easily computed. M is just rise over run. So I guess going from this blue point to this blue point, I rise up. I rise 5 and run 5, so m is equal to 1 in this case. I guess it tells me that y is equal to x plus 20. There's a relationship between x and y along that boundary curve in blue, not the parabolic curve in black below. So I guess the answer to my question, come in. And interpret x of I in terms of y sub I with that relationship, but I think it just simply gives me y sub I minus 20. I think when it comes to the amount of pressure exerted on a horizontal ice sliver way up high, it doesn't change. It's still my rho times my g times the d sub I, but in this case, it's still 1,000 times 9.8 times my 30 minus y sub I. I think when it comes to the force exerted on an ice sliver, it's still going to be nothing more than the product of the pressure in the area in terms of that ice sliver. I think in this example, that turns out to be a 2 times 9.8 times 1,000 times a y sub I minus 20 times a 30 minus y sub I. Oh, I forgot my delta y. I'll put it in. I'm sorry, I'm running out of room. So that the total force exerted on at least that upper portion can be interpreted as a definite interval upon taking the limit of a Riemann sum. Let's put it all in. I'll pull out my constant if you guys don't mind. I got an integral, which in the integrand's position has a y minus 20 times a 30 minus y. And I'm integrating respect to y. Did I miss anything?
No.
Got to go back then. So my balance in terms of extreme y values go from, yeah, not down there. I'm going to look at the isosceles trapezoid portion up here. My y extremes are from 25 to, oh, cheapers, got it. Now, I know you guys, I've run out of room on the board, but can I just talk my way through answering the question completely? Now to find the total force due to hydrostatic pressure on this particular plate, this particular facade, I need to take the evaluation of these two integrals and add them together. So when you guys do that, what do you prefer? You guys, I don't know where you're coming from. Do you prefer joules or Newton meters?
Same.
Which one?
Same thing.
Which one?
The same thing.
Which one you prefer?
Joules.
Neither. Neither. This is a force. The units are newtons. I'm just saying, keep track of what you're dealing with. We're not dealing with work anymore. Right? Okay. I think I said a lot today. Can we get some practice? Or do you need practice? Yeah, you do, because we have this on the exam quiz. By the way, that's it. What I discussed tomorrow will not be in the exam.
Sweet.
Is it gonna be big enough?
Video file.
Yeah.
I've emailed video files before.
Really?
Yeah.
Okay. Yeah, I can do that.
You can do that.
You guys, I'm kind of nervous. I just think there's a lot here. If you're feeling nervous about your level of expertise and after this homework set, just go in and dive in and do the evens as well. Do the evens as well. If you're not feeling confident with where you're at. I'm just kind of nervous. It seems a little light.